Okay. Hello, a warm welcome to our Q&A session from Erlangen. The first series, Basics of Protection, comes to an end. In 7 sessions, we talked about what is a protection, how do we define a protection scheme, which protection principles do we use, what is an earth current, what are primary or what are secondary values, how do we build a protection scheme. And we discussed also the topic reliability in protection. Then we went further into selectivity in line protection. How does it work in a non or directional overcurrent protection, or a distance protection, a differential protection, and then we finished it with transformer or busbar differential protection. We are very pleased with the high level of participation and hope to have awakened your enthusiasm for protection technology. And believe me, we received a lot of questions. We went through all your questions and selected some of them for the Q&A session. I just want to apologize that we can't answer all questions right now. Please keep in mind that we will answer all questions later on via email. And if you have dedicated questions for protection functions, settings, or your specific applications, please, there are 2 options. Contact our global customer support, which is available 24/7 all over the world, and also go for further trainings look at the Power Academy website, and then you will also get additional training here. But before we start answering your question, I'm happy to announce a special offer from Siemens Power Academy to you. All bookings of protection standard trainings until September the 13th, 2024 will get a discount of 10% on classroom training and even more, 20% in virtual classroom trainings. Both trainings, presence and virtual, include many practical exercises thanks to the intensive use of the CPROTEC digital twin. And now it's time to start answering, and Siegfried and I will answer your questions step by step.
Yeah, welcome also from my side. We have arranged the questions a bit according to the structure of our lectures. So we start with questions on the first webinars, Basics of Protection. And I combined here a few questions dealing with current transformer. Answering them in detail would, I think, take at least an hour. We know current transformer issue is really an important issue for protection. And for that reason, we are currently preparing a separate session on current transformers. And it will be available soon. And there I will explain the current transformer, the type of current transformer, and what happens during saturation a bit more in detail. So the answers on your questions here will be a bit shorter. The first one is, what will happen if the fault current exceeds 20 multiple of the CT ratio for a 5P20 current transformer? So the 20 means it has a dedicated accuracy of 5% up to 20 times nominal current for nominal burden. And if the current exceeds that limit, we may have a bit saturation, but it also depends on the burden. If the burden is lower, we can have a higher current. And on the other hand, if we have a DC component on that, we can already have saturation with much lower current. So you see, the story is a bit more complicated. And for that reason, the advice I can give you at that point is, in all protection relays, we have dedicated CT dimensioning rules. They are shown in the manuals, and they give you a guideline how to dimension your current transformer. How do you decide when to use 1 amp or 5 amp? It's a bit traditional. In some areas of the world, you have majority 5 amp current transformers. In other areas, you normally use 1 amp. From the protection point of view, 1 amp is the better solution because the currents are lower, you need less cross sections in the wiring, and the burden is lower. But the protection relays are designed for both. What is the CT class that is more accurate or suitable to use for a distance protection? There's no general answer possible on that. One thing is, must be clear, the upper separation of CTs is you have to divide CTs in measurement CTs and protection CTs. You must be sure that you connect the protection relay to a protection CT. Below that, you have different classes. All of them can be applied with distance protection as long as you observe the dimensioning rules. It's worth highlighting the details of CT class for differential and saturation characteristics. Yes, that is a thing we are going to do in that separate session, in a separate webinar, which will be available soon.
That's also a question for you now.
Yeah, that's a question on star point earthing. When do we use reactance earthing? How do we decide which type of earthing to use? Also there, this chapter of earthing, especially these systems where we have no earthing or we have a reactance, a coil in there, it's again a longer discussion. Also there, we are preparing a session on that. So I will just give some general remarks here. The use of systems where the neutral is not earthed or earthed via a coil is mainly found in distribution systems, industrial systems, with earth fault compensation, also sometimes in subtransmission. That means in transmission, you always have solid earthing. In distribution, you find everything. That means there is no one thing which is the best one. It depends on the type of the system. If you have a very small system, like an industrial system, isolated neutral can have some advantages because the earth fault currents are pretty low. If you have overhead lines, a distribution system with overhead lines, also this isolated neutral for very small systems or earth fault compensation have some advantages because there you then have self-extinguishing faults. So that are the advantages. But these approaches also have some disadvantages. So it depends, and we will discuss that a bit more in detail in that webinar. What additional protections would be required in a system with isolated neutral? The point is, in a system with isolated neutral, a phase-to-earth fault is not a short circuit because there is no current loop. That means there is no big current flow there. That means the short circuit protection will not catch such a phase-to-ground fault. You can even continue operation with a phase-to-ground fault in many cases, but finally you have to find this fault, and that is the tricky thing in these systems. The short circuit protection will not find the fault. That means you have to install dedicated protection for this type of fault, and that is the additional protection we need in these systems. How this isolated earthing works, as I said, that will be explained a bit more in this additional webinar on earth fault detection in systems with isolated neutral or earth fault compensation. The next one is yours, I think.
Yeah, it's mine. It's a very short question. What is GOOS? GOOS stands for Generic Object-Oriented Substation Event, and it's an expression of the standard I61850. And it's a special part of the I61850 is the -8 of I61850. -8 describes the GOOS. And what is it? So the GOOS is a communication between the different parts of a substation, the devices between the substation. So what do you do with that communication? You typically do interlockings. You can exchange information between the devices. and based not on wiring, on parallel wiring. The whole standard is based on an Ethernet communication, and the goose is very on a lower level of communicating and uses now I forgot the name. So it's spreading out multicast, exactly, yeah. So multicast Ethernet-based communication based on the standard of I61850. Can you please explain what is goose? Okay, that's done. And latching in relation to the protection relay. Yeah, latching is mainly used, for example, for LED, or you can latch an information. That means you keep the information in your system even if the information disappears or the status goes back to zero. One example, if you latch an LED on your relay front for the trip or the pickup, and then after tripping, if it's not latched, then there would be no LED. So and later on the stuff comes into the substation and nothing happened, no LEDs is lighted. So then you could use the latched LED or the latched information. That means the stuff comes in after the trip or the pickup and see, in that bay, that relay picked up or tripped, and then they can go into directly address the device and go in detailed analysis and know where to go. That's the latching or unlatched information.
Okay, the next one is also for you, Gerd. The question is here, please clarify the necessity of the use of a battery in a substation. A substation is full of energy. Why do we need a battery there?
It's a good question. So at least the first thing of a battery is you have a DC voltage. And with the DC voltage, we operate the protection relay itself, but also we operate the binary inputs of the information, and we command circuits and also the circuit breaker. So all this equipment is controlled and operated by the DC voltage supplied by the battery. But you could also use an AC-DC converter and to have the DC voltage in your substation. Why do we use a battery? The reason is quite easy. Our power supply or our grid should also work in case of an AC failure of your 220 AC voltage. So if your local AC voltage fails, you should also have an operating substation. That's why you install a battery in your substation, and you have a safe and reliable power supply for the whole control of your protection system. Now, the next question is one for you, Siegfried.
Is it possible that an evolving fault can occur from single-phase to three-phase short circuit within milliseconds? Yes, these things happen. Faults often start single-phase. For instance, on an overhead tower, you have a lightning stroke. You have a phase-to-ground fault in one phase, and then around there it's getting hot. The potential of the tower will increase, and that may evolve to a two-phase fault. Or you can have a problem in a current transformer. The current transformer explodes and the parts flow away. That is a thing which is not very often, but it happens. And the protection relays must, of course, react to that accordingly.
Okay, the next question is also for you. It's about the unsymmetrical load conditions.
Yeah, in case of an unsymmetrical load, but not an earth fault, the sum of I1 of the three phase currents, I1 plus I2 plus I3 is not equal to zero. How can we differentiate between an unbalanced current and an earth fault? That's a good question. Remember, the earth current is defined as the negative sum of the three phase currents. And I explained that we have protection function working on the phase current that is shown in the upper part there. And we have special protection function the earth current protection working on the earth current. And both functions have the problem, they have to distinguish between normal operation and a fault. And if we look at the phase current, in normal operation, the current fluctuates somewhere between 0 and a maximum load current, whatever it is. That means we must do the setting above the maximum load current so that the relay doesn't pick up with load current. And the same idea applies to the earth current. Also there we have a smaller range of earth current, and that is the earth current due to unsymmetrical load. You see the green area in the bottom diagram is smaller. That means during normal operation we have, due to unsymmetries and some other effects, we see earth current in this range, and we must do a setting higher than that what we have in normal operation. And that is the way how we differentiate between unbalanced load and earth fault. In unbalanced load, we are in this green area. In case of an earth fault, we move to the right, we come into that short circuit area.
Okay, the next question is also a question to you, Siegfried. It's about the inverse time protection. I think you told me it's a little bit of tricky thing about them. That's a good question.
That one is a little bit a tricky thing. How do we deal with a time variant current on the inverse time protection? What is behind that question? Imagine you have a short circuit situation where you have a current flow seen by the relay, which would lead to a trip command delay of 1 second. That means in this curve, you would be somewhere between let me see where's the cursor? Oh, it has disappeared. Somehow between around 1.5 of nominal current. That means we have this current flow, we would expect a trip after 1 second. And now imagine after half a second, that means during this delay time, the trip would be in 1 second, but after half a second, suddenly the fault evolves and the current increases to a value where the trip time, let me say, would be half a second. That means now half a second is already gone. Now the current increases, and with a new current, we would have a tripping time of half a second. What is the protection now going to do? You could say, okay, now the tripping time would be half a second, and half a second is already over. I trip at once. That could be a possibility, but that is not standard in protection. Standard in protection is to do the same thing an electromechanical relay would do, to ensure a proper coordination, even if you have electromechanical relays there. What would an electromechanical relay do? You have an induction disk there, and in the first phase of the fault, this induction disk starts rotating, and after half a second, it has done half its rotation. And then suddenly the current increases, but now it means it still has half of the rotation left until it trips. That means it would start rotating faster, and that means of the new tripping time, half a second, 50% is already over, another 50% would then still be open, and it would trip after 0.75 seconds. And this mechanism that we simulate the behavior of an electromechanical relay in our software here, that is called disk emulation. And that is a standard in inverse time relays. It's implemented, you don't have to set it somewhere. You will find a setting for the reset. That means after the fault, how does the relay behave there? Are we also going to simulate the backwards rotation of the induction disk or not? That is a thing which can be settable. You see, it's a bit a complicated thing, which we tuned the digital relays to behave the same way as electromechanical relays, which still may be installed in a substation and they have to be coordinated properly. Sorry, that was a very long answer, but it's a thing which is often discussed. The next one is yours now.
Okay, there are two questions about the arc protection. What are the main benefits of having a proper busbar protection over just having arc protection in cable, switching device, and busbar compartment? It's a good question, but remember what is the main principle of an arc fault protection. So the topic is that you need at least an arc. So an arc flash must be somewhere visible, and then the arc protection can see it and can react. That means the arc fault protection will not react if there are faults where is no arc. You have some proper circuits inside the thing, inside your switchgear, or inside your CT where there's no arc that couldn't be detected by the arc fault protection. That's the one topic. So arcs have to be there. And the second is that a busbar protection, a proper busbar protection, would also, to be selective, would have this disconnector image. So where's the fault? Where is my feeder connected to which busbar, to have selectivity and to trip only the faulty part, and to have the selective tripping. So these are the main differences. So you see, an arc fault protection does not cover the full functionality and protection necessity of a proper busbar protection scheme. That's why the arc protection is typically used in medium voltage applications in these medium cubicles. Coming to the second question, is arc fault protection function typically available in SIPROTEC 5 series relays? Yes, it is. Since we have a modular system, you can add it to all devices. And what you see in the middle is our arc protection module, plug-in module. And this module can be plugged into these slots, which are there are always two slots available in the base module. If you need additional one, you can add another module where you can add an additional 3 of these arc flash protection cards. And every card has 2 channels. And what you see additionally on the picture is the black one is a so-called point sensor, and where you are dedicated, you have the sensor on one point, and the picture in the upper right corner is a so-called line sensor. So you have a longer section, a line with a lot of detection points, and then you could feed it somehow through your switchgear and detect arc flashes for a longer distances. So these are the 2 sensors, point and line sensors, are available as part of our SIPROTEC 5 protection system.
Yeah, the next one is a very short one. What is the expected life of a protection relay? When can we say it's old now? That's a good question. I can ask the same question for your car. When is your car, what is the lifetime of your car? So there are a few similarities in these discussions. A bit of difference is there. A protection relays is always on. That is a difference to your cars, but there are some similarities. It's designed for a certain lifetime, and we typically say 20 years, 25 years. It's a bit according also to lifetime of switchgear. Lifetime of switchgear, there is no electronics in there, tends to be longer. So you can say, as a rule of thumb, switchgear has something like 40, 50 years. And during the lifetime of a switchgear, you do one exchange of the protection. That means our estimated lifetime is 20, 25 years. Of course, that is not an exact thing, like in your car. The point is, if devices become older, the failure rate increases. It can work without any failure even for 30 years, but if you observe, let me say 1,000 relays, and you make statistics how many devices fail, you will see that you may get an increasing failure rate. And the important thing there, it of course also depends on the operating conditions. For instance, if you install the devices in a permanent hot area, where they are permanently running at the temperature limit, that will decrease the expected lifetime. If you operate them in a clean, air-conditioned place, it will be better for the lifetime. So it's important for a company to think about what is the replacement strategy. That means if you have 1,000 relays, you must have a certain strategy to have a regular replacement, because you need a certain amount of staff to do the replacement, so that you don't end up in a situation where you suddenly have to replace 50% of your relays in 1 year, and you won't have enough staff for that. So that means must be planned to a certain extent.
Yeah, and also if you notice higher failure rates on a relay series after some years, then there's also discussion. You are active in changing the whole substation to have again new relays in the whole substation, or to do a kind of ad hoc service all the time. If something happens, you have to go to that device, have the right spare part, do it. And as we protection engineers know, when does it happen? It typically happens 2 o'clock in the night. It's raining and dark. And so that's, if you notice some topics and the strategy and your strategy, how to exchange, it's into our experience, it makes sense to think about, to plan it and exchange the relays of a whole substation.
Okay, that was the lifetime of relays. The next question is on
one for you.
Redundancy concepts. Remember this drawing here? I use this drawing to explain a little bit the different redundancy concepts we have. Always have in mind, as protection engineer, we must always make up our mind what is going to happen if we have a short circuit and one protection relay which should trip this short circuit does not work for any reason, or the breaker doesn't work. There must be always a backup. And then I use this slide here to show the different concepts we have. And the upper one is the main 1, main 2 concepts. And the first questions relate to that. How does the main 1 and main 2 concept work? Will both initiate tripping? How about priority? Yes, theoretically, you have 2 possibilities. If you have 2 protection relays working in parallel, you could make an OR function and an AND function. You could either say, I will only trip the breaker if both relays want to trip, or you could say, every relay can trip the breaker independent of the other one. And as we are talking here about redundancy, we take this concept. That means in the main 1, main 2 concept, both protection systems can work independent of the other one. Both can trip, so there is no need to discuss anything about priority. The fastest one will trip first, and the other one will trip maybe 2 milliseconds later, give a trip signal to the breaker, but at that moment the breaker is already opening. Does redundant line differential with backup distance as main 1 and main 2 make sense? Yes, it makes sense. The important thing is, we offer line differential protection with distance protection included. That means we have a certain degree of redundancy already in one box. But be careful, that is not a main 1 and main 2. That means you should not use the differential in one relay as main 1 and the distance protection in the same relay as main 2, because then you have no redundancy in case the device fails. That means what you often have is, for instance, as main 1, a distance and differential in one box, and as main 2, another distance protection. That means if one of these relays fail, you still have one full protection working. If the communication link fails, and that is often a bit part which is subject to disturbances, if the communication link fails, then you lose the distance, the differential protection in one device. But if you still have a distance protection there, you still have two distance protections working as main 1 and main 2. So this concept would make sense. What is the criteria assigning a relay as a main or as a backup protection? If we go away from this main 1, or the principle of main 1 and main 2 is both react selectively and fast. If we have a main and a backup concept, that means the main protection acts in a selective way. That means there we guarantee that only the affected cable or transformer or whatever is tripped. And if that fails, if the backup relay trips, we accept then maybe a longer delay time, or we also expect some limitations in selectivity. That means we trip more than necessary. We trip not only the affected line, but a few lines more. So that is a balance. The main 1 and main 2 concept is the best concept because it guarantees full speed and full selectivity, even in case one device fails. But of course, it's also the most expensive one. If you come down into distribution, you have to look for more economical solutions, and then solutions where you have main backup, where you save some money with the disadvantage that in these rare cases where a short circuit is there and the protection fails, where you have a bit longer delay times or a bit unselectivity. Shall we use overcurrent protection as backup if differential protection failed or if fault is in external zone? Yes, it is a typical application that we use overcurrent backup together with line differential protection. Remember, a distance protection or an overcurrent protection has an automatic backup for the next line. They also look into the next line. A differential protection looks only into its own line. That means together with differential protection, we must install a separate backup protection that is often an overcurrent protection. And that, of course, will be a backup not only for its own line, it will also look on the next line, but also there it will only react if the differential protection on the next line would fail.
Okay.
So now we come to the selectivity chapters, and the first one we have there is on the timing. I think that's
it's also
again
a topic for you.
my one.
I will take the next slide.
What is the pickup time? The pickup time is the time from the fault inception until the contact which indicates a pickup closes. That means it's the reaction time of the device. So we need a millisecond for the data acquisition, and then internally we have some algorithms running. They need a certain data window, and that leads to a certain reaction time until the relay really is sure, yes, I see a fault, the current is above the setting value. And all delay times you set in a relay are always added to that. That means if you set a delay time of, let me say, 100 millisecond, the total trip time will be a bit longer than 100 millisecond because the timer only starts after this pickup time. Now, of course, you could ask the question, now, if you know your pickup time, why don't you subtract it from the delay time? It looks easy, but think about changes of fault current, evolving faults. Pickup time is not a constant thing, so we said, to keep it clear, the timer settings you do are always delay times will be added to that, to the pickup time. The second question, instant tripping time, is shown as 0 milliseconds. Again, in this case, the 0 milliseconds means we do not add additional delay. After we have decided the fault current is now above the setting value, 0 millisecond delay means at this point we are now going to trip. Shouldn't it be some value? Shouldn't we add some value, 20 to 30 milliseconds, in order to avoid nuisance tripping? I remember in old times people sometimes did that, but according to our philosophy, it doesn't make sense, because the pickup means we are now sure that the current is above the setting value. And if you want a trip with a current above the setting value without a delay, you can set it to 0 millisecond. Due to the algorithms we have now, it is not necessary to add some safety milliseconds to allow the algorithm to review its decision. If we say pick up, we are sure that the current is above the set value.
Okay, there are some questions about these principles of overcurrent protection and directional overcurrent protection. What does relay drop-off mean for relays 2 and 4 for the parallel protection system shown? So we copied that picture into the slide, which is meant. So we have these two lines, these parallel lines, covered by or protected by 4 protection relays. 2 are non-directional, so relay 1 and 2 are non-directional relays, and the relays 3 and 4 are directional relays showing the direction of the infeed. And then shown is a fault on the line on the line 1. What will happen? So the relays will pick up. We have the relay 4 will not really pick up because it will see the fault in backward direction. When we draw that slide, we assume that there is some overcurrent protection in the relay active. So that's why we assume that it will pick up anyway. But to be correct, in that shown example, relay 4 wouldn't pick up. So we have a pickup of 3 relays. Okay, what will happen then? The relay 3 is the shortest one, with no delay time of 0 milliseconds, will trip and will clear the fault from the infeed coming via the parallel line 2. And that opening of the circuit breaker here will react in a drop-off. That means the pickup will be taken away. So the relay 3 will no longer pick up that fault.
And that means the timer will be
stopped.
Reset.
Exactly. So drip-up means our 300 milliseconds timer will be stopped. And then the fault is only fed by the infeed coming via relay 1. In that relay, the timer is running, and after this grading time of 300 milliseconds, the relay 1 will also trip, and the fault will be cleared. And what is essential, the line 2 will be still in operation, and all customers on the outgoing feeder are supplied, even in case of that fault on feeder on line 1. Then a second question, I have doubt in last topic, which is directional overcurrent protection. How the middle relay will react when fault occurs on one side. So we assumed the one side, it's that you still mean that you're talking the fault will be here anyway, and what will happen with the relays in the middle. So the first thing is, let's see about the direction of this relay, the directional overcurrent. So which relay will pick up? So of course that relay will pick up, it's a non-directional, it's fed from here. Then the relay 2 has a direction to the fault, it will pick up. The relay 3 will not pick up, since the direction is the relay sees the fault in the back in the back direction, so no pickup. Here there will be a pickup, and for that relay 5 will not pick up, but relay 6 will pick up at the same time. That means all relays without relay 3 will pick up, or not in 5. So 3 and 5 will not pick up, and the other relay will start their timer. And then we have the timer. So the first relay which will trip is the relay 2, which has a 0 milliseconds delay time. So that will be, the circuit breaker will be opened, and that will result in the drop-off of the pickup relay 4 and 6. And of course the timer will be stopped, so no trip will come in future. And after longer grading time, since we have a longer line, the relay 1 with a delay of 600 milliseconds will clear the fault on the left side. I hope that was the background of that question, what will happen with the relays in the middle during that kind of fault.
Now we come from overcurrent to distance protection. And the first one there is, again, a pretty complicated question. Remember when we discussed the principle of distance protection, we had a look at these different cases, the normal operation, a metallic fault on the line, and a resistive fault. And we measure the complex impedance and plot it in such a plane, that is the complex impedance plane, where the horizontal axis is the resistive part of the measured reactance, and the vertical axis is the reactive part. And if we have a fault on the line, we are somewhere here on this red line. If we have a fault at the end of the line, we measure a point here, and we have a fault on the next line, we measure something there. And in normal operation, of course, the relay measures the impedance the whole day. In normal operation, we measure something here in this area where it says normal operation. Now let's read the question. R load, that is the measured impedance here, is a summed resistance of whatever is connected on the other side of the line. Now we measure here into the network, and I've just drawn here this equivalent impedance, which is just a representation for everything behind the line, to whatever is connected to the other side of the line. But our load is not constant, certainly not on the other side of a high voltage transmission line, where our load can be an entire city. So our load will change. So how does the distance relay handle the changes of our load? Yes, it's completely right. This operating point will always somehow run along here. If during night, if the load decreases, it will go more and more to the right. If the load increases, it comes closer. And that is the thing the distance relay sees the whole day long. It all the time measures the impedance. But as long as this measured point doesn't run into the characteristic, it has no effect. The relay measures the impedance, checks is it in the characteristic or not. That means the fluctuations of the load point around here doesn't have any impact. The only thing you must be very careful about, as soon as you run, and this lower part shows the full characteristic we have, as soon as you run into characteristic with load, then you start the timers, and then typically, at least after a second or after a second and a half, you will trip. And that is a thing where you must be very careful with the setting. These fluctuations here, as long as you are outside, have no impact.
Okay, that leads to the next question. If we have our selective zones, what is the significance of the pickup zone and why do we need it? So in the previous relay series in CPROTEC 4, there was really a dedicated pickup zone, and yeah, Siegfried just mentioned it. So the pickup zone, as soon as your calculated impedance run into that pickup area, all timers of the distance protection function will be started and will run. That means, yeah, you have to really be careful what is your pickup zone. In CPROTEC 5, there is no dedicated pickup zone. We just used a very easy rule. The greatest zone, in that example, the Z4, will be our pickup zone. That means as soon as one of our calculated impedance runs, it covers somehow that zone without the load cut off. So that is cut off. So if we run into here, all distance protection functions will start their timers. And if the impedance or your load would remain in that section, then the distance protection would trip according to the set time for that zone. That's the topic of pickup zone or distance zone. So we take the greatest zone as a pickup zone for CPROTEC 5.
Yeah, and we designed here this load cutout you see here for the cases where you have trouble to do the proper setting, because with heavy load, you typically are in that area around the axis. That means you can set the outmost zone very large, but to avoid this load encroachment, we call that, you cut out a little bit here. That means in a heavy load situation, you can run into the characteristic here, but as long as you are in a load cutout, it will not start the timer. So it gives, for some cases, additional possibilities to do the setting and to be sensitive. On the other hand, the disadvantage is we get a few more parameters and get a few additional pages in the manual, but that's the thing we have to deal with in distance protection.
Yeah, and that's why we are protection engineers. We need some new parameters to talk about it.
Okay, what is the difference in Mo and quadrilateral characteristics? I mentioned we have two types of characteristics. On one hand, this rectangular, or it's not rectangular, it's a parallelogram with this load cutout. And you also find in a lot of applications these circular characteristics. We call that Mo circles, or it's a polarized Mo circle. You see it's not around the origin. It's polarized with a little bit difficult equations behind that. What is the difference? I think the main difference is, except the fact that one has corners and the other one is a circle, the difference with respect to protection is, in a quadrilateral characteristic, you can make the setting in X direction and in R direction independently, whereas here you can set the circle, just the radius of the circle. Remember, what was the rules for the setting? We have to do the setting in X direction according to the reactance of the line. That means this setting here of the first zone is typically 85% of the reactance of the line, and the same applies here to the circle. That means we define the radius of the circle according to the length of the line, if we talk about the circle of the first zone. And here. And now in a quadrilateral characteristic, you can independently set the fault resistance you want to cover. That means this distance here, how much fault resistance do you want to catch, can be set separately, whereas if you have a Moe characteristic, it comes with the radius of the circle. You can't set it separately. And that makes a difference, especially if you have short lines. Because if you have short lines, the X setting is shorter, the radius of the circle is shorter, but on a short line, you can have the same fault resistance than on a long line. That means basically the reactance setting and the resistance setting are two independent things, and especially for short lines, it makes sense. You have the reactance setting and you make the resistive setting wider, so this rectangular thing looks a bit not like a square. The resistive length is longer, and that is a thing you can't do in a Moe characteristic. That means the quadrilateral characteristic in this respect has some advantages concerning setting. So now the question is, why do we still have Moe characteristics? In many applications, especially in many countries where you traditionally have Moe characteristics, they are in use. People are replacing maybe old relays by new relays. And now if the new relays have a completely different characteristics, that would mean people have to recalculate their settings. They have settings which define the Moe circles. And if they get new relays, they want to say, okay, I take my settings and I'm happy with the settings. I can catch all faults I want to catch. Take these settings, bring this in the new relays, and they don't want to recalculate the settings. And that is the reason why we offer both alternatives in the relay, so that this replacement of relays is pretty easy.
That's also for you, Siegfried?
It's mine as well.
Yeah,
okay.
Yeah.
We
discussed about that.
that was a figure concerning intermediate infeed. That means we have here the situation, we are talking about a backup situation. That means this relay here looks after a fault on the next line in a backup case. And there I explained if we have between the relay and the fault an intermediate infeed from a power station here or a part of the network, this influences the measurement. And now the question is, how do you account for intermittence of renewable power plant? Yes, that could also be a renewable power plant, but also a normal power plant. The effect on the intermediate infeed will vary along with the time. Yes, it is, and we have to live with it. That means the effect of this intermediate infeed is not a constant thing. It could be completely away if this power station is out of service, then you have no intermediate infeed, or it could be very strong. That means the influence or this effect of intermediate infeed changes. That means also the reach of the second zone. How far does this relay look into the next line will unfortunately change depending on the infeed. That is not nice, but we have to live with it.
And especially in the medium voltage grids where we have more and more distance protection and also more renewable infeed. So that's an interesting issue. But distance protection will be required to get the pickup criteria.
So now we're coming to the last part, selectivity with differential protection. And the first question we picked up there is a very general question. What about cybersecurity of distribution and transmission protection systems? That is a good thing, and a lot happens there that has one general aspect and one line differential specific aspect. Let's first of all look at the general aspect. Cybersecurity is an issue of increasing importance in our relays. Clear, as long as we had electromechanical relays, it was no problem. As long as you have digital relays without any remote access or any communication link, it's still not a big issue. But as soon as you have communication links, especially if you have IP communication, as soon as you want to have remote access to relays to read out some information or even do some setting from remote, you have to think about cybersecurity. And that was one reason why we decided to start the CPROTEC 5 range of relays, because if you want to implement proper cybersecurity concepts, you have to do some preparations on the hardware side to be able to store certificates in the relay, to do certificate handling, also software packages to do that. And with these things, we are now able to offer a lot of cybersecurity features, but it's always a system question. That means in the relay, we offer a lot of functions you typically need for cybersecurity concepts, but you have to do the concept for your whole substation, for your whole installation. And one issue dedicated for differential protection. If you line differential protection needs communication between two ends. If you have an optical fiber, a dedicated optical fiber, you have no big risk. But if you go with your differential protection communication through an existing communication system, of course, that is part of the protection system. And if you have security issues in your communication system, in your company communication system, which is used for the differential protection, and for instance, you have to stop it or to reconfigure it, then you must be aware that you kill the differential protection if the communication is gone. So then it has an additional importance for differential protection.
Okay. Differential protection, exactly two questions about the differential protections. We need communication, so both relays should be of the same brand, and both relays need to be from the same brand. It's the same. Need to be from the need. Should be or need to be. Okay, that's also a question we receive, and it's not only a topic of communication. So you take their independent relays, take one from that brand and that one from the other brand. Differential protection is always a protection system. So you have if you have a 2 or 3 end, the 2 or 3 relays have to interact with each other, not only communication, but also the algorithms which are implemented into the system, how to calculate stabilizing, how to calculate the differential characteristic, how to set up the communication. So think about ring topology or chain. So if you switch it, what will happen if a communication fails? So all relays have to be from the same manufacturer, from the same algorithms. But one good thing for CPROTEC relays, if you have a large installation of CPROTEC 4 relays and now you want to start updating to substation to CPROTEC 5 relays, so in the past you had to change on both substations, so the new side and also on the remote side with the old relays. With CPROTEC 4 and 5, you are now able to communicate with each other. So CPROTEC 4 can communicate with a CPROTEC 5 differential protection relay, and that makes updates for you much easier. You can concentrate on the change of the new substation and keep the existing one, the remote end, and later on can exchange there. So always keep in mind, differential protection is a system and not a combination of 3 single protection devices.
Okay, and that feature is not only required if you do relay exchange. You could also have a situation that you have a 2-ended lines with 2 CProtect 4 relays. And now if you are installing, for instance, renewable protection, you make a teat feeder,
exactly,
a tapped line where you then need a relay also on this new end. And there you could install a CProtect 5 relay, then doing differential with the existing 2 CProtect 4 relays.
Okay, that's one for you.
Okay, yeah, that's about the algorithms in differential protection. I explained the differential protection principle can be applied either using individual samples, or instead of using samples, you calculate phasors, complex phasors, and do the differential principle with phasors. Both concepts have some advantages, some disadvantages. And what we do in line differential protection is we use both. That means we have one algorithm which uses phasors. You can make this very sensitive. It's a bit slower because for the phasor calculation, you need some data window. And on the other hand, we have a fast algorithm. Theoretically, you can use individual samples, so we go a little bit away from that. That means instead of using individual samples, like in the busbar protection, we're doing an integration across a few samples. And if you integrate the current, it's called charge. And that's why this type of protection is called charge comparison protection. But it's very similar to these using of samples. So it's faster, but you cannot set it as sensitive as the other one. The other one with the phasor computation has more filtering. That's why it uses longer data window. The charge comparison cannot do that much filtering. So that works for the high current faults, and the other one works for the resistive faults where the fault current is lower and the speed is not so important.
Okay, so there's 2 further slides left which you prepared. So now one for the transformer differential protection. Will the 3-winding protection work in the same way as the 2-winding? Yes, it's just another winding which you have to set, so it works accordingly to the 2-winding transformer. Then what about the 5th harmonic blocking? So for the blocking, we used a second harmonic, so that's a second harmonic blocking which we typically use. And
for the inrush?
For the exactly about the inrush. And a second function for the inrush, we use this waveform analysis, CWA analysis, that looks at the pattern of the behavior of the 3 phases. And that typically these both functions run in parallel. And if this analysis of the waveform detects an inrush, it will block the differential protection. And to your question, what about the 5th harmonic? We use that 5th harmonic blocking, and we typically use for the overexcitation. So that's a criteria which runs into the overexcitation criteria. Yeah, I think that are the topics.
Then we are coming to the
last
one about busbar differential protection. First question, what is high impedance and low impedance in busbar protection? I must confess, I did not mention the high impedance busbar protection concept. That's a complete different concept. Maybe we should also produce a webinar about that. What you do in high impedance busbar protection is you take all current transformers, put them in parallel, and normally, as the sum of the currents are zero as long as the bus bar is healthy. You don't get a voltage at the connection point, and if significant differential current is there, then the voltage increases. That means you have a very simple concept where you just have to connect the current transformers together with a resistor and have a voltage relay at that resistor. And if that voltage relay picks up, you have a bus bar fault. It has, of course, some limitations. One thing is you get special requirements for the current transformers. And as soon as you have more complicated bus bars, it becomes also tricky because you need a lot of auxiliary relays. But for simple bus bars, it's a cost-effective solution. Why is it called low impedance bus bar? This low impedance comes from the fact that current transformers must always be operated short-circuited. That means you have a current transformers, you must not have the terminals open. If you connect it to a relay, you have a low impedance loop there. And the special case for high impedance is there you connect the current transformers a bit in a different way. And what is the difference between bay unit and central unit in a distributed busbar protection? You see that slide here behind me. You see here the bay units. And the purpose of the bay units is the data acquisition. That means we get the current sampled values from there. We get the position of the isolators. And we send all that to the central unit. We need one central unit where we run the equation. To calculate the differential current, we must sum up all the currents. That means we must have one point where this calculation is done. And that is done in the central unit. That means here, in this central box, the protection runs. And if that algorithm decides that we have a busbar fault, then we give the trip signal down to the devices so that they can then trip the breaker here. That is the distributed busbar protection concept.
Okay, so since we run out of time, we unfortunately must come to an end. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and training, or also remember you can access our customer support 24/7 for detailed questions on applications or special settings or on the functions. And remember, all bookings of protection standard trainings until September 24 will get a discount of 10, and for the 20% for the virtual trainings. Yeah, so thank you, Siegfried.
Was a pleasure.
For this great series, your great engagement and your support for the Siemens Power Academy, and also for this webinars for you as the audience. And yeah, it was really a great pleasure to work to you together. And look forward, we plan to continue this series. New topics are already on the agenda, so stay tuned. And now, stay safe and sound, take care, and goodbye.
Goodbye.